Okay, I guess we can start by me giving an introduction. Hi, everybody. Welcome to TC seminar. And today, our seminar is going to feature two excellent speakers from Locomotion. And the first speaker is Professor Hae-Won Park from KAIST. And our second speaker is Professor Ioannis Havoutis from University of Oxford. So Dr. Park is an associate professor in KAIST and the director of the Humanoid Robot Research Center. He received his bachelor's degree and master's degree from Yonsei University and received his PhD from University of Michigan. And before he joined KAIST, he did his postdoc at the Biomimetic Robotics Lab at MIT and then joined UC, where I became his first graduate student. So I had a lot of fun memory with Hae-Won at Urbana-Champaign, and he's a great advisor, and we were very productive at that time. And then Professor Park has won multiple prestigious awards, including the NSF Career Award, Earlier Career Spotlight Award from RSS Foundation, as well as IROS RoboCup Best Paper Award. So after our first talk, we're going to welcome our second speaker. Ioannis is a senior research fellow at the University of Oxford. His group is part of the Oxford Institute, Robotics Institute, and he received his PhD and master from the University of Edinburgh. And he worked on machine learning and control of articulated robots. And he has also authored multiple award-winning publications and has been a member of national as well as international projects. So without further ado, let us welcome our first speaker, Professor Hae-Won Park.
Okay, yes. Okay, so thank you for nice introduction, Anna. And then thank you for inviting me for this wonderful seminar series. And thank you for being here to attend my seminar. Yeah. Today, I'm going to talk about model predictive control for legged robot and from fast quadruped locomotion to agile climbing systems. So let me briefly introduce my lab and my research. I do research on legged robot, and I do control design for legged robot utilizing model-based control on the left, as well as reinforcement learning. So I started utilizing this reinforcement learning for my robot. And this robot is actually able to reach up to 5.67 meters per second, utilizing the reinforcement learning policy. And then on the bottom, we have another reinforcement policy. And then this reinforcement policy is designed by combining trajectory optimization and reinforcement learning. And its maximum speed was 6.18 meters per second, which is quite fast. It is a little bit slower than MIT Cheetah. And this reinforcement policy has a feature to make transition between the gaits, between bounding and trotting as well. And lastly, I do hardware platform and actuator design for my own robot. So these are the actuator design designed for our legged locomotion robot. So in today's talk, I will mainly talk about control design for these two robots. The first one is KAIST HOUND. This is the same robot that as you can see the previous videos. And then on the right, we have Marble, Agile climb legged robot. So KAIST HOUND is designed in-house, and it has a customized multi-module design. And it is 45 kilogram heavy, and its leg length is 68 centimeters. So this is quite large robot, about the same size of Boston Dynamics spot. The second robot is a Marble. This is actually a climb robot. So it is only 8 kilogram heavy. So it's actually designed by Yannan. And so in order to climb the vertical wall, it keeps with the magnetic foot. Okay? And this magnetic foot can provide adhesion force to the ferromagnetic surface. So it provides in normal direction 530 Newton, and then in the shear direction it can provide 430 Newton. And this magnetic foot is designed by Yongwon and Jae-Jung Park, which are my students, who are my students. And this magnetic foot, we utilize the electropermanent magnet, and this electropermanent magnet can turn it on and off the magnetic force like this. But unlike the electromagnet, it does not need any electrical energy to stay on state of the magnet. Instead, it requires only it requires electrical energy only when switching the on and off state. And on and off switching occurs within 5 milliseconds, which is pretty fast. So this magnetic foot is designed for fast locomotion on vertical wall and inverted wall. So these two robots has a different purpose. The KAIST HOUND is designed for running on ground, while the Marble is actually designed for climbing vertical surface very fast speed. But it shares the same simplified single rigid body dynamics model, okay, with different inertial parameters. The only change we should make is actually foot contact constraint. So KAIST HOUND is actually it has to respect the friction cone foot contact constraint, while the Marble should respect some foot constraint imposed by magnetic foot. So because these two robots share the same simplified model, so probably the model predictive controller would be a good choice for design the controller for this robot. So in this single rigid body dynamics model, we have rotation matrix, which is in SO3 manifold. So normally this SO3 manifold is represented by Euler angles, and MPC is designed utilizing Euler angles. But as you know, this Euler angle has some significant issue when it comes to singular position. And you can see that the gimbal lock happens in singular position. So in just the normal quadruped robot, this would not be an issue, but this robot has to climb vertically and work on ceiling in inverted configuration. So it can easily pass the singularity configuration during this locomotion. So we have to take into account the rotation matrix very carefully. So we formulated our nonlinear MPC as an optimization problem on SO3. This is error, and this is a force constraint. And where the state variables are as the following, which include rotation matrix. So this nonlinear optimization on SO3 manifold can be converted to optimization on vector space utilizing reparameterization using retraction map. And this optimization gradient, analytical gradient, and Gauss-Newton Hessian can be obtained utilizing the method presented in this Hae-Won paper published in 2016. So this optimization problem solved with the SQP solver and utilizing our QP solver. And this is a whole control architecture. And this is the learning experiment with the speed of 3 meters per second. And this is a push recovery experiment. As you can see, it can recover from the push very well, even though the push is very hard. And if you see the robot recovered from the push, it actually can slide on the very slippery wooden block. So now we designed the MPC for quadruped robot, and then we can actually transfer this robot to design climbing robot controller. And this can be very easily done by changing only this foot contact constraint to take into account magnetic foot. So we have a condition for sliding, prevent sliding, and prevent peel-off. And then the foot contact constraint will be the intersection of those two constraints. And this is actually the MPC experimental result. So this is a pacing gait with the speed of 0.7 meter per sec, climbing vertical wall. And this is inverted trot gait on ceiling with 0.5 meter per sec. And this robot can carry 2 kilogram payload vertically, and on the ceiling it can carry up to 3 kilogram payload in inverted configuration. And because this robot is in a quadruped form with lots of degree freedom, we can actually design some trajectory which can overcome some obstacles. So this video shows the robot overcome 10 centimeter gap and then 5 centimeter high obstacle. And it can actually switch it between it can make a transition between the surfaces. And then we did some outdoor experiment on water tank. So as you can see, even though the water tank is covered with rust and dust, the robot can climb up vertical wall with quite fast speed. So even though we designed some MPC controller for these two robots, we actually experienced a very catastrophic failure during the treadmill fast run experiment. So in this experiment, you can see that in slow speed motion, robot step onto the side rail, which is not moving, and robot actually stumbled over. And in this situation, probably it's better to change the gait sequence. So since our MPC has only fixed gait sequence, it doesn't have the ability to adapt to this kind of disturbances. So now I switch my gears to talk about contact implicit model control, which can adapt to gait sequences. So here we have an optimization problem, and this optimization problem we use differential dynamic programming to solve this optimization problem. Now I try to incorporate contact model inside of this dynamic model. And this contact impulse will be function of x and u, and it's the solution of this optimization problem. And this optimization problem will have a constraint which consists of a linear complementarity constraint and Coulomb friction constraint. And because of this constraint, the solution can be categorized into 3 types. First one is separating, second one is clamping, third one is sliding. And then we can obtain gradient, analytical gradient of contact impulse with respect to arbitrary variable for each cases. But in the case of clamping, because we actually enforce the post-impact velocity equal to 0, it's a post-impact gradient of post-impact with respect to arbitrary variable will be always 0. And this actually can result in local minima. So if you see this problem, you can see the reference position is higher than robot. The optimal solution would be the robot should repeatedly jump to match the reference position. but robot could not jump. So this could be some types of optimal solution, making the repeated jump. So to remedy this issue, we replace the linear complementary constraint with a smooth constraint, where this zero is replaced with some positive variable rho, which is said to be a very small value. So as rho decreasing, this smooth constraint will be approximating the original constraint more closely. So this rho could be some adjusting parameter. So if we use just analytical gradient, you can see that robot does not jump. And this paper proposes some heuristic rule to calculate analytical gradient. But you can see that this robot, this motion is kind of aperiodic. And then you have this repeated jumping motion utilizing our analytical gradient with smoothing. So this shows some simulation result. This is hopping robot, and this is reference trajectory. As you can see, without any reference trajectory, with this simple reference trajectory, this NPC can discover the gait. And this is a planar robot, planar quadruped robot, and it can discover some gait. And next is actually very slippery slope. So you can see that robot sometimes slide on the slippery surface to catch the reference trajectory. And this is we can actually make the NPC to prefer bounding gait. Okay, so you can see that it's actually discover automatically the bounding gait if we have a preference on the gait. And this continuous flipping is also possible. And you can see that we actually look at the effect of smoothing variable rho. So if rho is too small, so you can see that it's actually very close to original constraint. It does not jump. When we increase rho, then we will have a jump, but it's actually, it has a very long stance time. If we have a rho, rather rho, then it can have some repeated jump. And then you can see that the cost is lowest in this point. And then if the rho is too high, then it does not make jump again. So we can see that there is some sweet spot for the value of rho. So this rho is actually adjusting parameter for our MPC. And this is show on effect of the rho for different tasks. And we extended this method to 3D model. And here on the left, we have a gait symmetry preference with a diagonal pair. We only have a cost for gait symmetry. And then on the right, we have a gait symmetry with the same side pair, and it will the pacing gait emerged. And this is an unstable reference pose. So of course, the robot cannot stay on this reference pose. Because it's actually not equilibrium point of the robot, but the robot try to match that unstable reference pose. When it fails, it automatically kick the ground to match the reference pose, as you can see here. So this is an experimental video of our MPC. So in this experiment, there is no swing leg trajectory, explicit swing leg trajectory, and then no contact detection algorithm used for control. And then the experimenter only give joystick commands. And then we have gait preference trotting, and MPC DT is 0.025 second, and sampling time is 0.025 second, and then number of horizon is 20. So as the experimenter give a joystick command, it started working. And it's increasing the speed. So this is actually very preliminary result. So as you can see, the robot sometimes skip the gait because we did not enforce the gait. We only provided preference for the gait for trotting. And as you can see, NPC solve time within the sampling time, most of the time. Next experiment is unstable configuration experiment. So likely we have no swing leg trajectory and then no contact detection algorithm for control. And as you can see, robot tries to match this unstable pose. Okay, so this is actually a very preliminary result. So we actually trying to improve the controller performance more. Okay. So in conclusion, we used the model predictive controller to design a controller for two different robots. The first one is running quadruped robot, KAIST HOUND, and then next one is agile climbing robot, KAIST Marble. So MPC was flexible enough to control different robots with very similar modification. But because MPC has some planned for sequence, and then it doesn't have ability to adjust the gate sequences in our MPC, so it needed some improvement, and then we are trying to make this contact implicit MPC more robust. And then this contact implicit MPC can discover automatically some interesting gait in our robot, but it needs actually more experimental verification, and it needs to be more robust to be implemented in real robot. So this is the end of my talk, and then thank you for your attention.
Thank you, Hae-Won, for the great talk. We're going to move on to the second speaker, but at the end of the talk, we're going to have an extended discussion session where people can save their questions towards the end. We're going to have a very nice discussion. So without further ado, Ioannis, if you're ready, you can share screen.
First of all, thank you so much for the invitation and the introduction, Ioannis. So it's always a great pleasure to present to colleagues, and I will tell you more a bit about my work with learn optimization today. So I will try to focus mostly on how we have worked to marry learning-based approaches within optimization frameworks. And I want to ask you in advance to be patient, because I've prepared a few more slides than I should have. So I'm going to fly through a couple of slides really fast. But of course, if you have any questions or want me to sort of dig into more details in some slides, just ask at the end. Right, let's get started. Most of the work in my group is about tasks that are usually performed by humans. And we're looking at how these tasks can be automated and performed by robots. In this case, starting with the bigger picture in this form feels more like preaching to the choir here, but the general point that I'm making with this slide is that we've seen how robots have really helped us revolutionize the way we work in the past. And now we're seeing robots sort of enter new domains that are a lot closer to working with humans. So in this case, with the current robotics sort of development, nowadays we require sort of highly mobile robots that are much more versatile. They're not that sort of one purpose-built robots that operate in automated warehouses or logistics facilities and so on. So we need a lot more in terms of capabilities in order for them to be successfully deployed. In building up these capabilities, my group and myself have been working in the past decade or so into three main components. And these are the sort of three main components of our research. So combining optimal control with machine learning and motion and path planning approaches. So we tend to work in these areas, and we're looking into how we can combine this into different levels of behavior and motion generation. So to make robots with arms and legs truly useful. Right, these are the robots that we've been mostly working with. All of them are quadrupeds. Most of them are in the size of a medium-sized dog. So you can think of it as a golden retriever type of robot. And we've been looking at these robots for the capability that they have to maneuver and travel through spaces that are very hard to navigate. So really for complex and unstructured and challenging environments, like manufacturing floors, mining tunnels, nuclear power plants, and so on. And the challenges that we face in these environments is that we have a lot of different surfaces to locomote on. You have concrete, gravel. You have bits of a facility that are generally very slippery. You have other bits of the facility that might have gravel or sand and so on. And these are kind of challenging aspects of locomotion. And of course, these present with very strict requirements for very high degree of mobility and flexibility. Lately, of course, we've been looking a lot at how we can combine manipulation capabilities with sort of robotic platforms. And in that respect, we've been looking at how we can have these robots autonomously interact with valves, but push buttons, operate control boxes, gates, so on. And these are also skills that can easily transfer into different environments as well. So these are skills that from an industrial environment can transfer to a service environment or even a domestic environment. And this is kind of work that we are doing in parallel with the HSR robot, a mobile wheel-based manipulator for the RoboCup at home competition that we take part into. And the main idea here is that for all robots to be truly useful in such environments, they need to be good at three main capabilities: mobility, interaction, and autonomy. Today, I'll focus mostly on mobility, and I'll hint a little bit on our work in autonomy, in interaction, but I will not talk about our work in autonomy. So on mobility, we've been working on leg locomotion for quite a few years now, and we have developed a plethora of approaches that span the full range from sampling-based or search-based approaches to trajectory optimization and machine learning. And nowadays, most of our effort is either combining optimization with machine learning or working into sort of more pure machine learning approaches for locomotion as well. And these are the two approaches that I'm gonna focus on mostly today. I'll start with a framework that we developed over the course of a couple of years now. That's called RECALL. To give you the sort of bird's eye view of the framework, it's RECALL stands for Receiving Horizon Experience Control Adaptive Leg Locomotion. And sort of you have the robots in the right. You have a planner that is a non-linear optimizer in a receding horizon manner. You have a couple of initialization choices, how you initialize the optimization. One of them is a kind of a heuristic-based one, and the other one is a neural network one that I will talk a little bit more in detail in the following slides. You have an input that would be either a joystick input, so sort of input from a user or from a higher level planner that would command the robot where it needs to be. And then you have sensors that would give you things like, for example, height maps or vision estimates and so on. And at the end of this sort of pipeline, you have a whole body controller that in most cases should be a model-based approach to producing the required torques for moving the limbs of the robot. So in that framework, we start from a kind of well-known optimization framework that has been developed in the past by colleagues in ETH. So they said trajectory optimization problem. We work with a direct collocation formulation, and we utilize a single rigid body dynamics model for that optimization. It's very straightforward, sort of done with polynomials and splines, and then you can use an optimizer like an interior point method solver also to sort of control how the splines, the control points of the splines behave, and then you arrive at trajectories for your robot to follow. So starting from the original tower framework, what we quickly discovered is that the solutions that this produced were not in a range that our quadruped could reliably execute. So we started adding costs. One of that would be an integral cost for the base. So we penalized how much the base would swing and bob laterally and in the pitching motion. We added terrain costs to help that reach the surfaces where you have sort of desired footholds and avoid edges and so on. And we added more costs on kinematic constraints. So, for example, we instead of using simple box constraints for where the end effect where the feet of the quadruped can lie, we used the super quadratics that have this sort of ellipsoid shape that help us sort of target better where we want the legs to be at. And we've also utilized a sort of more a simplification of the terrain cost. So in essence, an approximation of a running terrain cost that avoids abrupt changes in the cost function, which all kind of resulted in an approach that can easily navigate over relatively complex environments, and that we can then look at how we can make it into a receding horizon formulation. By adding all these cost terms, though, we've increased the computation time that it would take to solve for this for the optimization. So what we started considering was how we can learn part of this equation, in essence, to have an approximate model of the analytic solution, and then use that when we run the system online. I've seen in the audience a couple of people from that were part of the memo project. So this is kind of how you can use memory of past experience in order to speed up your current solutions, how you access current solutions, or how you optimize faster. We first started with learning a dynamic stability criterion. So the idea here was that we can calculate these analytic stability margins based on how the terrain looks and how the configuration is at this point. The problem is that we couldn't really perform this calculation online. So to be able, instead of trying to do the calculation online, we've collected a bunch of data and we've learned an approximation of this margin, and then we've used that to, in essence, produce estimates of that online. And here we can see how this is overlaid over the terrain that the quadruped is working on, and how it changes with respect to how the morphology looks. The next major bit that we looked at is how we can create more efficient initializations. The key observation here was that when you initialize your nonlinear optimizer by a naive approach, then your solutions would vary quite a lot, with a lot of them sort of being solutions that the quadruped could not realize with the real hardware. So what we started doing is we started collecting data in simulation of trajectories that of good solutions, of low-cost solutions, and then we wanted to create a library that we can then easily sort of very fast be able to query to get good initializations. And the learning initializations provide the full sort of solution to a trajectory. Most of the time would give you a good trajectory to start with that would have some, let's say, details along the way that would need to be ironed out by the nonlinear optimizer. So some of the samples that we could sample from the network that does this approximation would be able to run on the system as is, but in most cases they would have some sort of point where they would not work that great. So we would pass them to the optimizer as a good initialization, and we would see at the end sort of the difference between what we predict and what the optimizer gives out. The problem with this is that this was a unimodal approximation. So we would start from a grid where we could sample trajectories, and then we would learn sort of how a good trajectory looks, like a low-cost trajectory would look, and how a trajectory with higher cost would look. And then the system would approximate sort of good trajectories in that cost sense. Right? We could even iterate that in order to make sure that the system does not produce poor initial guesses. And then, since this is something that we could run offline, we could iterate a couple of times until the system does not, until the system converges. So what we're able to show in this case is that with the sort of heuristic initialization, we would get a lot of failure examples, but with the learning initialization, we have a lot less failure, and we have also trajectories, whole body trajectories that have much less cost and are better realized by the real world hardware. And you can see that here in these results, we can also show how this increases or decreases relative to how many iterations we allow the optimizer to run. Taking this also one step further, we've worked on to how to, in essence, provide initializations for the receding horizon formulation. So as the MPC loop is unrolling, then we can have a system that now is not unimodal anymore, but it's a multimodal system, neural network that generates trajectories as initializations for the optimizer. And here we can see how this on the left, you can see sort of data that we've used to offline train that multimodal system. And on the right, you can see how we can use this online to, in essence, warm start optimizations. Of course, the main benefit of warm started optimization is that at the end you can get a lot better solutions with a lot less iterations. So this means that you can run your optimizer in a loop that is a lot faster, and you can achieve a higher frequency solver. And these are examples of how this looks with a real system, and how the sort of cost landscape looks, and how the reference trajectories for fit and so on look. And this is another example with a little step for the quadruped and so on. Now I'm going to talk a little bit about the work that we did on learning-based locomotion. So this is work that we've been doing in parallel, and it's a really straightforward application of reinforcement learning setup. So in this setup, we ask the robots to follow an input that is a velocity input, so a linear velocity for the base and a yaw rate for the base. Right? So this is just a joystick that commands where the robot needs to go, and we would like to train a control policy that is able to orchestrate all the degrees of freedom of the robot in order to follow this control input as closely as possible. We drew a couple of parallels with the optimization-based framework in the sense that here we also introduced a key set of constraints that serve to kind of guide the optimization. This is work that we did back in 2020, and you can find more information on the paper that I'm pointing at here. So one of the key benefits of the system was that we were able to bootstrap, in essence, from examples from an optimization-based framework, and then have a controller that we can, in essence, refine on by using the RL framework. What this means is that in using that, we arrive at a learning-based controller that starts from a good solution to the problem, and we can see that it can do a better job. It can do as good a job as the controller where we started from, and we can do the same. We can achieve the same sort of robustness and flexibility with even just a smaller amount of torque required on average to run. What is more, we've looked at how we can then transfer this to the real robot. And what we're looking here is to be able to characterize the behavior of the system in a way that would make sense for in a sort of in guaranteeing that the system would be performing as predicted. And of course, in reality, we cannot give any hard guarantees in the sort of analytical control sense. But what we've looked at here is we looked for statistical guarantees, looking at how many constraint violations we had in simulation, and then estimating that, and then looking at how many constraint violations, for example, we would have on the real system, on how the joint acceleration violations would look on when running this on the real system. And by making this really closely match, we are confident to say that this would be as performant on the real hardware as it is in the simulation, where we can run a lot more examples and we can get a lot more statistics. So this is how this looks on the real system. So you can have a really naturally responsive system that is also very compliant. It generalizes well in environments that are well beyond what it has trained on, and all the training has been done in simulation, right? I need to stress that. And in the bottom right video, we have an example of where we artificially make one of the knee motors sort of behave as it were damaged. We decrease the sort of proportional gain of the motor by a lot, so it does not really follow what the controller is trying to do with it. But we can see that the system can still manage to function and perform a crawl gait in response to a user input. The next step on that work was to add perception, and of course this is kind of a more extensive framework here. This is not a single policy that is commanding what the robot is doing, but we have a couple more sort of neural networks that are at play here. I don't have really that much time to go into detail, but I want to point out that with this case, all training was done in simulation, and stress that the key benefit here, sort of in contrast with the more sort of traditional control-based approaches like MPC and so on that we have been developing, is that we cannot very easily perception information to these sort of frameworks. So in this case, we've added first of all training in a procedurally generated environment, examples of which you can see at the top right. And then this also contains perception information that goes into the system. So the system now makes exact sort of decisions about where it would want to place its next foothold. And of course, this works quite well on the real hardware as well. So you can see some examples of the system going over sort of some of the kind of mobility benchmarks that we've used earlier in the lab. And then you can see that it's also a very on the bottom right. This is a really reactive controller, so it can take a lot of sort of hard pushing and remain very stable. And of course, this would generalize well beyond the lab environments. And one other aspect of that work to stress is that all of the training has been done with a different quadruped. So all of the training of this controller has been done on the previous version of the animal quadruped, while we were able to deploy robustly and successfully with a bigger robot, something that is very hard to achieve with non-learning based or non-learning sort of supported approaches. Right. Given that I'm running out of time, I'll skip that a bit because it does not that much to the discussion, and I'll directly go to the third and last, I promise, topic that I want to cover here. So this is our latest and greatest work that we will present in Predictive, and this is kind of I want to use it as a way to kick off like a broader discussion in the community. So here's one problem. You have a very slippery surface. This is a whiteboard that we've sprayed with water with soap. So we have the robot to walk on that, and we would want it to be balanced and sort of robust over different levels of slippiness. So when we're faced with these problems, especially coming from a control background, intuitively we think about how we can maximize robustness and reactivity by increasing the motor control frequency, right? The counter argument to that is looking at how biological counterparts do that, and I will give you a moment here to appreciate this absolutely outstanding performance by this dog that is really flying through the obstacle course, the agility course here. So the example is here, right? The mammalian quadrupeds are very agile, they're very robust, and their behavior is really reactive. But if you look into the hardware, you see that they have really high sensory motor delays, and of course high sensory motor noise as well. So if you look through the literature, you can see that, for example, a dog at the size of the quadrupeds that we have, about 40 kilos or so, they suffer from actuation delays that are estimated to be about 60 milliseconds or so, which breaks down to sort of sensor delays, sort of material nerve conduction delays, synaptic delays, and so on, down to sort of fourth generation delays. So the question here is how these systems are able to cope with all that noise and delay and be able to be that performant and that robust. So we wanted to see whether we can reproduce that, or maybe have a sort of slight peek of whether this can be something that we can use as inspiration for quadrupedal locomotion with the hardware that we currently have. So we started looking at policies that run at really lower control frequencies. All the work that I've shown you this far is executed at a frequency of about 200 hertz, give or take. And now we were looking at whether dropping that even as low as 5 hertz would be able to result in locomotion behaviors that made sense. Of course, what we used for this work was again a learning-based controller with a system that is not even deep. It's a really simple sort of neural network that we train with observations that are very simple, like base orientation, angular linear velocities, joint positions, velocities, the sort of desired joint positions from the previous tick, and then the user input as in sort of the command, like the joystick input that we use with all the other controllers. what we discovered is that with a really low frequency policy, we can have really robust behaviors. And these are robust behaviors even when we change the base mass. We play around with the gravity or the friction or at external forces, external torques when we're running these controllers. In essence, we've set up a simulation benchmark, and then we see how these systems perform when you have policies that we on which we do dynamic randomization or not. So dynamic randomization is one of the kind of really general kind of ways of doing sim to real, kind of making sure that your policy would transfer to hardware by randomizing sort of all sorts of dynamics parameters in your training environment. And then we also see that these lower frequency motor controllers are less sensitive to actuation dynamics when we change the actuation dynamics in deployment. And also, for example, when we introduce artificial latency in the actuation dynamics, we can see that the lower the frequency of the control, then the higher the robustness, up to some extent, of course. We in our study we also see that these policies train at least as fast as the sort of higher frequency policies and a lot faster than the sort of very high frequency policies. And we've also observed that the difference is also qualitatively very pronounced. So you can see in the low frequency locomotion policies, you have very pronounced foot swing and stance durations as compared to sort of the higher frequency policies that intuitively we would think would be better suited for these tasks. To give you an idea of how this works on the actual robots, here's a couple of examples at different control frequencies in the lab. And you can see that, I mean, with the 5 Hertz, it takes a little getting used to with the user to sort of command the robot around, because it does not follow your commands that accurately anymore. But we posit that the sweet spot for such a robot would be somewhere around 10 to 25 Hertz, something like that. And we saw with a 20, I think all these examples here are run with a 20 Hertz controller. We can be very reactive, very robust. We can deal with very slippery terrain. We can do high-speed locomotion. So this is in the bottom left. We do 1.5 meters. 1.5 meters per second locomotion with the animal C. We can do steps and work outside and so on. This is preliminary work. We've put quite a bit of effort into making this open and accessible. So if you want to have a go and test it out, you can go to the project website and to try it out and check out the project. Is as simple as clone, install, and run it. And you can see for yourself how this behave with different robots and different control frequencies, and how also the intricacies of training between different control frequencies work. Right. I won't spend that much time on what's next. I'll just say that we've been working a lot into transferring these approaches to local manipulation and whole body control. We've been working towards generating a benchmark for industrial tasks. We've been looking at how this can be accurately modeled, and we're also thinking of open sourcing that benchmark to the public, so we can have ways of evaluating different approaches. And in future work, we're looking at more learning, and we're looking at word models and semantic segmentation to with a view towards mobile manipulation. I want to take 1 second to thank all the wonderful people that have been involved and have made this work possible. and also the places that have funded this research that have made this research possible. And with that, I'll thank you very much for your attention and open the space for questions.
Thank you very much for both speakers. And now we can start our discussion sessions. And I'll kick it off with a question to Hae-Won. So Hae-Won, you mentioned about that in order to avoid the local minima, the parameter rho is a quite important thing to do. And could you give us some intuition on about how this is related to, for example, the ground stiffness, and how the value of rho is going to affect the simulation fidelity once you transfer to Ryzen and transfer to hardware?
Okay, so I think it's too early to say something about the law because we have not published the paper and this is a very preliminary result yet. We are trying to write a paper out of this, but this is actually not yet validated data. But actually the law is not related with the soft contact or anything. It's just a smooth version of linear complementary constraint. So this is something like the interior point method for solving the quadratic programming. So in interior point method, when you solve the quadratic programming, you actually kind of relaxing the inequality constraint. So it's actually very similar technique. The only difference is we do not actually tighten the law to the zero because we couldn't find the good way of scheduling the law to zero, actually not yet. So somehow the fixing the law to some upward value provide a better solution for us for now. So but I want to emphasize one more time, this is actually very preliminary result. Yeah.
So I guess I'll jump in with a question. So I had a question for Ioannis. When you are running the low frequency MPC here, you said you're also using a impedance controller to track that low frequency signal. So how fast is that impedance controller running under the hood?
At 200 hertz.
Okay.
So the assumption is that even if you provide your controller with references for joint position and velocities at a lower frequency, there is a controller under that is tracking that. So there is a tracking controller underneath. It's the same for the full spectrum of frequencies that we tried.
Yeah. Cool. Thanks.
May I, Mr. Chairman? May I, Mr. Chairman?
If you have a question, please proceed with your question.
Yes, I have a question for Ioannis. Ioannis, thank you very much for your excellent presentation. I have a general two questions. In general, in case where the trajectories are a solution of a dynamical system or a system of a differential equation, have you studied the stability of these solutions? And what kind of solvers you use? Are the solvers good in order to tackle stiff equations or things like that? And the other question is this: in general, for the optimization problems you use, have you ever considered the case to study, to count, to find all the number, to find the total number of solutions in order to choose the almost optimal solution or optimal? I think just a general question.
Right. With regards to the first question, in In other words, we've looked at how we can evaluate the solutions that are produced by the neural networks with looking mostly at stability with ZMP. So for example, we have a trajectory that is being produced by the neural network, and we look at the stability in a ZMP way, and whether the, at the sort of discretization points that we choose for the produced trajectory, ZMP says you're dynamically stable, then we consider the trajectory dynamically stable. In the case that I presented, there was no such evaluation in between, because these were mostly used as a way of warm starting the optimization. So if there were aspects to the trajectory that were not stable, this would be ironed out by the optimization step. Now, for your second question, Mikhail, we haven't really thought about this. I'm not sure how one would go about at producing many solutions. Yeah, on top of my head, I cannot think of a way of producing multiple solutions. Unless you are thinking of having sort of a discretized sort of a grid of potential footholds, and then you consider a set of footholds, for example, something like that. This is kind of approach that we've seen sort of being very successful now, right?
Yes. Ioannis, we have our methods with Konstantinos. We have our approach that he would like to cooperate with us. We can tackle this problem. In general, there are robotics. I've been to in Riyadh, Sophia Antipolis, and there are many robots there, like a Stewart platform and things like that, and they know the exact number of solutions. And in this case, but we have our approaches with Konstantinos, so that we can, if you're interested, we can find the total number of solutions for a particular problem, and to study the almost optimal or almost optimal cases.
Absolutely. Konstantinos, send me an email.
Okay, we'll send you an email, and for the other case, we have also our method for trajectory to find the trajectories by solving systems of ODEs and dynamical systems, and in this case we have good solvers to handle it. We're able to find the stability and to find the okay. We'll send you an email with Konstantinos. Okay, Ioannis, thank you very much for your excellent presentation. Thank you very much.
You're welcome. Hope you've been polite. I think it was quite rushed. I tried to fit a lot.
Curious, are you training your policy to be robust to a range of sensory motor delays or to one sensory motor delay?
We're not training the policy to be robust to sensory motor delay explicitly. What we're doing is we're training at a different control frequency. So
it's not that the different control frequencies represent a type of domain randomization. It's fixed.
Yes, exactly.
Okay.
There's no domain randomization there.
So do you think that, have you tried doing domain randomization on that? And do you
provide absolutely.
Additional robustness?
Yeah. Yes, it does. It doesn't make that big of a difference, surprisingly, especially with the low frequency controllers. Our kind of running hypothesis is that with the lower frequency, the system is kind of forced to act more as a planner within the configuration space rather than a controller that kind of with the high frequency it behaves more more like a controller. I know that's maybe not very clear, but we're still working through it as well.
So I guess my question is, do you think it's just a matter of learning efficiency in a sense that the delays make the learning easier, and so you're finding a better policy, like you found a better policy faster? If you then like used that as an initial guess and then went to the higher frequency training, do you find a better policy yet, or is there something that's just inherently better about low frequency?
So to address your first point, we try to scale the length of the episode so that the training is comparable. Because if you train at a 200 hertz frequency, you get like a snippet of what is happening compared to training at 5 hertz, right? 5 hertz, your rollouts are much longer. So we try to account for that. So it's not. I mean, it's not clear yet. We're not sure.
It's super interesting. Looking forward to seeing.
Exactly. Yeah, we're very excited about this. But yeah, that's one point. There is a qualitative sort of step, maybe more of a continuous change when you sort of turn the knob down to the lower controller frequencies. The system acts differently, and we're trying to get to the sort of root cause of what this acting differently means.
Thanks.
Carlos, can see your hand up.
Yeah. Hi, Ioannis. Nice talk. Can you hear me? Well.
Yes.
Yeah, I have also a question regarding this low frequency training. So yeah, I mean, I have this point of animals, and actually it's very interested to look into this. But so animals have serious elastic actuators, and I believe you train with the rigid body attention when you were doing your simulation. That's correct. So
yes.
So
all of the training is done in Rising.
Yeah, actually, I want.
We use. Go on. Yeah.
Yeah. No, actually, I'm wondering. Perhaps you haven't worked on this, but I'm wondering what are your thoughts when we do this with passive dynamics, a really soft robot, not like animal. What do you think it could happen?
I think it would help. I mean, this is it's a stab in the dark. It would help. No, the reason why I'm saying that is that the literature about how mammals deal with that is that they sort of lean a lot on the compliance of the system. That's kind of what's keeping everything sort of robust.
Perhaps a question that could help a bit is another question on this topic is: have you tried to deploy this in robots like Unity as well? So if you have done this, are you seeing a difference in terms of sync to real between animal and Unity robots? Or
we have not tested on the A1 yet, but this is something that we are sort of it's on our to-do list now. But yeah, I don't think that we'll see that big of a difference, to be honest. Though it might be more challenging in the respect of the sensory noise, and that's why we are planning on doing that. Go on.
Thank you. Yeah.
Cheers, Carlos.
If anybody else has a question, please just unmute yourself and ask.
I would have a question. Hi, I'm Johannes, not Ioannis. I have a question to both Hae-Won and Ioannis. I have pretty much no experience in RL. Do you guys use a parameterization of time or phase in your learning? For example, in the 5 hertz, but also for Hae-Won for the MPC related, like hot starting RL policies or like the corresponding feedback. So do you use like time or phase information?
Ioannis, you want to go first?
Sure. In the current work that we've done, we have not used phase information, but I know that there are a couple of works out there. One would be in the animating avatars or even quadrupeds in for animation or computer games.
Yeah.
That uses face information with really impressive results.
Mm-hmm.
So I remember that we looked at it, and much of the sort of difficulty that we had was getting good coming up with sort of good starting trajectories for the system to train on. Nowadays that might be different, but we have not revisited that. Though I know that there exist works that are very impressive that use such information.
But still, you end up having periodic gaits that result from not having a phase information in it.
Right.
Thank you. And Hae-Won? Hae-Won, how about yours? Your setup?
So you asked about phase and time, right?
Yes.
Okay. So I mean, to be honest, the details I think my students know about that.
Okay.
And actually, this the controller that I showed in the second slide of my presentation is actually it's very similar to Jaemin Hongbo's reinforcement learning, the concurrent learning, which is published in RAL. And then I think if I look at the paper, it doesn't look like it's utilizing the phase information, I think.
Yep.
Yeah. So I think the in order to have some meaningful gait in the RL, actually we need a lot of reorder tuning actually. So and then my student actually went through very painful ego-adjustive reorder tuning to get meaningful gait. Actually, the first emergent gait was actually looks like plonking for high-speed running.
Yeah.
And then we actually could not reach to like more than 5 meters per second. So maximum speed was about 4.7 meters per second with the plonking gait. And then actually I gave advice to my students that you should make the gait more look like trotting.
Mm-hmm.
And then if I started trotting, it actually could reach up to 5.7 meters per second.
Yeah.
And then the second reinforcement learning, which actually combined with the trajectory optimization, is actually completely different idea. So we actually did the trajectory optimization over bounding and then trotting.
Mm-hmm.
And then we actually pulled out a lot of trajectory consist of trotting and bounding. And then we have about like 100,000 of gait trajectories. And then we actually pre-train that with the encoder and decoder structure. And then we use that for adding to add like reinforcement learning on the pre-trained encoder and decoder structure. And then the gait now was able to obtain both bounding and trotting gait. So this is another reinforcement learning that we are working on. Yeah.
Mm-hmm. Thank you very much. Very interesting.
If I may, I have a final question to Ioannis. So I haven't seen your work on learning the initialization for MPC. It's pretty interesting, and I'm curious to know on how do you handle the change of terrain? So because you need to give an input like how the terrain looks like, the optimizer to start giving a solution. So how do you handle this? Because it's not very trivial to handle.
Yeah, exactly. So there's a parameterization that we use for that. But in essence, gives you has a look ahead window, and it would tell you whether you have flat ground or what sort of differences in height you have in in a sort of grid manner. So you can think of it as a height map.
Ah, okay. So you actually give like a height map as an input. Okay.
Yeah.
Okay.
Yeah.
Okay. Thanks a lot. Also for the nice talk.
I have a question, Ioannis. What kind of noise you use for simulations? Additive or multi? Because if you use additive, this is not proportional to the function value. So
Yes.
if you use, for instance, Gaussian white noise with zero mean and things like that, maybe you have to use not additive. Okay, what kind of noise you use?
To be honest, I don't know. Maybe Carlos knows what type of noise you get in Rysim.
You have to use multiple because this is proportional to the function value. If it is additive, the noise, and the function value is large, then the simulation is not good. So
absolutely,
you have
I understand.
to put the function value 1 plus the noise strength in order.
No,
we have papers to send to you with Konstantinos. Okay.
I know that in all the simulators that we use there is noise. At least I can sort of confirm that. But in most cases we don't play with the noise value. Rather than what we do for dynamic optimization is we would change aspects of the environment itself, but not the noise. So we would change, for example, in some cases the masses of the parts of the system, the lengths of the parts of the system, or we would change the gravity vector, or add sort of noisy terrains or different types of terrains for the system to work on. And sometimes this can also be in a blind locomotion. You do that sort of noisy terrain and see how the system performs.
It is very important to handle noise. It's very important for the application.
Absolutely, yes, I agree.
So in this case, you have to try together to find the optimal value of the noise, the optimal strength, and to say for this case the noise strength is this, and for this application, we can do this together with Konstantinos if you like. Okay.
Sure. Yeah.
Thank you. Thank you, Ivan.
Thank you too.
Cool. So I think we can wrap up this seminar talk. And I would like to thank both our speakers today, Ioannis and Hae-Won, for two of very excellent talks on behalf of TC co-chairs and associate co-chairs. And before we go, I have a quick announcement to make. We're going to have a social event at ICRA preliminary on the Thursday at the conference. A couple of our TC co-chairs and associate co-chairs will be there. There'll be sponsored social events. So please look out for any announcement on our social media, including Twitter, YouTube, and our website. So yeah, so thank you for joining us today.